Hello there, Mr. Sutton here with the AB Calculus 4.4 Classwork Extra Practice Solutions on concavity. To figure out where this function is concave up and concave down, we start by taking the first two derivatives. First derivative is going to be cosine of x over 2 times a tail of 1/2, so 1/2 cosine of x over 2. And then second derivative, we're going to have negative, and then we're multiplying by another half, so this is going to be negative 1 over 4 sine of x over 2. And at this point we have to figure out where this thing has critical values. So set it equal to 0 and solve. So this is going to equal 0 wherever sine of x over 2 equals 0, if we just divide both sides by negative 1/4. And then sine of x over 2 is going to equal 0 wherever y is 0 on the unit circle. So looking at my angles here, at some point this x over 2 means I'm going to have to multiply all my answers by 2. So if I find answers between 0 and 2 pi, I'll end up having answers between 0 and 4 pi after I multiply everything by this 2. So places where sine equals 0, well, we've got 0, and also at pi and 2 pi. And we could keep going, but if after 2 pi, anything you multiply by 2 is going to be bigger than 4 pi, so we're not going to care about it. All right, multiplying all these by 2 to actually get x by itself, we've got 0 again. This is going to now be 2 pi and 4 pi. All right, let's put these on a number line, an f double prime number line, and let's graph it out. So we've got our endpoints at 0 and 4 pi, and then we have the only critical value in between those, because these were both critical values, but in between we just have the 2 pi. Doing some sign analysis in each interval now. Let me test out pi in there. So I'm plugging this into the original f double prime here. So I've got, let's see here, pi over 2, which is going to be, let's see, 90 degrees basically. Sine of pi over 2 is going to be 1, but we're multiplying that by negative 1/4, so that all comes out negative. And then if I do something between 2 pi and 4 pi, like 3 pi, well, when I plug that in, that becomes 3 pi over 2. Sine of that is normally negative 1, but it becomes positive after I multiply by the coefficient. So I see here that I'm concave up on the interval from 2 pi to 4 pi, because that's where f double prime is positive. And then I'm going to be concave down where f double prime is negative on the interval from 0 to 2 pi. For this problem, I want to figure out where the graph of this quartic polynomial is concave down. So I need to take a look at where the second derivative is negative. So let me find the second derivative. Y prime, I need the first derivative first. Y prime is going to be 12x cubed minus 48x squared plus 48x. And then that last 48, ironically, is gone because it becomes 0. And now let me take one more derivative to get y double prime. So that's going to be 36x squared minus 96x plus 48. And what can I do at this point? Well, I need to figure out critical values. So let me set that equal to 0, and I'm going to do some sign analysis once I find those critical values. So it looks like I can factor out a 12 would come out of all these. That would leave me with 3x squared minus, let's see here, this is going to be 8x, and then plus 4. All that equals 0. So now I need to do some factoring. Or I could use quadratic formula, but factoring will probably be a little faster here. So I know for a fact that I'm going to have a 3x and an x. There's no other way to get 3x squared in this factoring business. So now we just need numbers that multiply to 4, and then when I multiply them out with the 3x and the x, it all adds up to negative 8x. Well, let me think here. Only so many things multiply to 4. Now, I know that the things both have to be negative because they multiply to a positive and they add up to a negative. And let's see here. If I had negative 1 and negative 4, well, let's see, I'd have 12 and 1, or I'd have like 3 and 4. None of that's going to add up to 8. How about if I have 2 and 2? Let me try negative 2 and negative 2. So 3x times negative 2 is negative 6x. We have another negative 2x. That adds up to negative 8x. Eureka, I think we found it. So then our critical values for this first parentheses, if we add 2 and divide by 3, that's 2/3. And the other critical value for this parentheses is 2. Putting those on our number line, this is a y double prime number line. We've got 2/3 and 2. And now some values in each of these intervals. If we test out, let's see, 0 is a good one that's less than 2/3. That gives us a negative, so positive. Between 2/3 and 2, 1's a good one to try. So that would be, let's see, 3 minus 2 is positive, 1 minus 2 is negative, so negative overall. And then finally, bigger than 2, we try out 3. That's going to give us a positive here and a positive here. Now we wanted concave down, so that's where y double prime is negative, and we see that that is in the interval between 2/3 and 2. So that's going to end up being in standard inequality notation, 2/3 less than x less than 2, choice E. On this problem, we have some function f that is continuous on the closed interval 2 to 4 and twice differentiable on the open interval from 2 to 4. They're telling us that f prime of 3 is exactly 2, and f double prime of x is less than 0 on the open interval 2 to 4. Based on that, we want to know which could be a table of values for f. So this is a little bit tricky here. The key on this one is figuring out how much the f function has to go up by along these different intervals. And we have an interval from 2 to 3 and also from 3 to 4 that we can kind of track how much f is growing. Now the key on all of this also is that they told us f double prime is negative. Well, that means that f prime itself must be decreasing along this whole interval from 2 to 4. And we can go a little bit further. Since they told us f was twice differentiable, that means that not only does f prime exist along this whole interval, but it's also continuous because its derivative exists. So based off of that, we can figure out how much we need to be growing on these intervals. So if f prime of 3 is exactly 2, that means before we get to x equals 3, on the interval from 2 to 3, that means f prime has to be more than 2. Because if f prime is decreasing, if it gets to 2 when x equals 3, that means it must have been more than 2 before we got there. So that means that our original function, has to increase by more than 2. Now we don't know any exact values of f prime between 2 and 3. All we can really tell from this table is the average rate of change. But again, we know that f prime is continuous and it's decreasing the whole way. So if all the values of f prime before we get to x equals 3 are bigger than 2, then the average rate of change also has to be bigger than 2. So, which of these tables have functions that are growing by enough? Well, if we have to increase by more than 2, choice A here, we're going from 2.5 to 5. That's an increase of 2.5, so that's good. In table B, we also have a 2.5 growth from 2 to 3. That's also going to work. But in table C, we're only going up by exactly 2. Same thing with D, 3 to 5. That's a growth of only 2. That's too little. And E is even worse. We only go up by 1.5. So based on the fact that we have to increase by more than 2 on the interval 2 to 3, we can eliminate choices C, D, and E. Well, it's down to A and B. And the only difference between these two is that A is going up by 1.5 along that next interval, while B is going up by 2. Now, on the face of it, both of these look to have f primes that are decreasing as we go. However, if f prime is decreasing and it's exactly 2 at x equals 3, that means on the interval after that, on the interval from 3 to 4, f prime has to be less than 2 along that whole interval, which means that on the interval from 3 to 4, f of x has to increase by less than 2. Well, taking a look at these, only choice A is increasing by less than 2, not B. That's going up by exactly 2. That's too much, so that means then choice A is our final answer. For this problem, we want to know when f of x equals 2x times e to the x is concave down. So for this, we're going to have to figure out when f double prime is negative. So we have to start by at least taking the first derivative, and then we'll go from there. That's going to require the product rule in this case. So getting my box and ribbon out, I've got factors of 2x and e to the x, whose derivatives are, we've got just 2 and e to the x. Using the ribbon to multiply that back out, that's 2e to the x plus 2x e to the x. And now I have to keep going. So f double prime now, I'm going to go term by term and take the derivative. So I've got a derivative of 2e to the x, which is also 2e to the x. That's nice. Now I have to take the derivative of 2x e to the x. Well, hold on a sec. Didn't we just take the derivative of 2x e to the x? Yeah, we did when that was the original function. Well, if we're now taking the derivative of this expression as part of something bigger, it's still going to give us the same result. So just looking back at our box and ribbon, we again have 2e to the x plus 2x e to the x. Same result that we got the first time around. All right, so let's clean this up a little bit. If we have 2 of these e to the x's, we can combine that into a 4 e to the x. And now I need to figure out critical values for this so I can figure out exactly where it's negative. So let me set this equal to 0. Now, in solving for x, one thing I can do here is factor out an e to the x. I can also take a 2 out of this. So if I factor out 2e to the x from all this, that's going to leave me with just 2 for that first term, and we'll have, let's see, just x for that other term. And all this still equals 0. Now, using our zero product property, one of these things at least has to be 0. 2e to the x, since it's an exponential function, cannot ever equal 0. So we don't even have to worry about that piece. But 2 plus x can equal 0. It's going to equal 0 subtracting 2 here when x equals negative 2. So that is our only critical value that we will do our sign analysis around. So here is my f double prime number line with my critical value of negative 2. And I'm going to plug in a number less than negative 2, like negative 3. And I'm going to plug it into this simplified f double prime expression right here, this already factored expression. Now the nice thing about this expression is that this 2e to the x part is always going to be positive no matter what, because it's an exponential function. So really all that matters is this 2 plus x for determining the sign. If I have 2 plus negative 3, that's going to be a negative. And then something bigger than negative 2, I like 0. 2 plus 0 is a positive. So now we see that our f double prime is negative on the interval from negative infinity to negative 2. So therefore, the graph of f is concave down when x is less than negative 2, which is going to give us answer choice A. For this problem, f is a function whose derivative is this f prime function here. We want to know on which intervals is f concave down. All right, well, I basically need to figure out where f double prime is negative, and this is a graphing calculator problem, so I can use the grapher. But before I can do anything that's helpful, I need to figure out what the second derivative actually is, so I can graph it out. They gave me the first derivative already, so be careful here. You don't want to take 2 derivatives. You've already got f prime. You just need a single derivative at this point. So f double prime then, just taking one derivative, that's going to be 3x squared minus, this will be 10x, plus the derivative of e to the x, which is also e to the x. And we're going to figure out where this equals 0, find critical values, and we're going to do that on the grapher now. So here I am on the grapher in my y equals. I've entered f double prime as my y1, and I'm going to need some kind of window for this thing. So looking at my answer choices as a guide, because they didn't give me anything else, the smallest finite value here is about 0. It's pretty close to 0, and the biggest value is a little bit less than 3. So just to be on the safe side, I'm going to make my window -1 to 3, just so I can see the y-axis clearly. So let me go -1, and then I've already got 3 as my x-max for whatever reason, so hey, we'll take it. Let me do zoom fit, and let's see what this thing looks like. All right, so we're crossing the x-axis in 2 places, and again, I want to figure out where this function, this f double prime, is negative, because that's going to give me concave down. So here's the graph. I'm going to need to figure out what these 2 x values are so that I know what interval I should say my function is between. Now, just looking at this here, it kind of looks like this is pretty close to 0, so it's probably 0.116, and this is pretty close to 2, so it's probably 2.062. And if I'm out of time, I'm going to pick choice C, because that's the best looking answer. But I have some time here, so let me actually go ahead and find those exact values on the calculator. So let me do second trace, and option 2, zeros. My left bound, let me find the first 0 here. It's a little bit close to the origin, so let me do enter to a little bit to the left, move it to the right, press enter again, and enter one more time gives us about 0.116. So that's that first value, which we kind of anticipated, but it's nice to get confirmation. And then we do second trace zeros again. And this time I'll move a little closer to that other 0. And let's see, enter, move to the right of that 0, press enter one more time. Third time gives us about 2.062. Again, not a huge shocker based on the answer choice, but it's good to see it. So again, I'm looking for places where f double prime is negative. that happens on the interval from 0.116 to 2.062. So that means that f itself is concave down across this interval. So that's going to give us choice C. For this problem, we have this f function shown above here, and we want to know which of these statements about f is false. So most of these are going to be true. We're trying to find the false one. All right, we'll just go through and see what we can prove and what we can't prove. Choice A, f is continuous at x equals 0. Well, from the left and the right, we're approaching the same value, and the function exists there. Everything matches up. There's no holes or breaks at x equals 0, so visually it definitely looks continuous. So I'm going to say this one's true. On to the next one. F is differentiable at x equals 0. We have a cusp at this spot, or at least a sharp turn here. So because we have a cusp there, that is known to be a non-differentiable spot. So this is a false statement, and if we wanted to, we could go ahead and pick B and be done with this. But it's always good to look at the other options if you have time, just in case you missed something and there's something even better waiting for us. So choice C, f has a critical point at x equals 0. Well, critical points happen where f prime is either 0 or undefined. And we just said in part B here, or choice B, that f prime is undefined. It's not differentiable at this spot. So because f prime does not exist at x equals 0, this is a true statement. We have a critical point there. D, f has an absolute min at 0. Well, yeah, this is the lowest point on the graph, so that's also true. And then the concavity of the graph changes at x equals 0. So we go from being concave down between -2 and 0 to being concave up like a cup from 0 to 2 for x values. So that is a concavity change, so this is also a true statement. So then the only false statement definitely was choice B, and that's what we're choosing. On this problem, our function is defined as this cubic kind of thing here. We want the largest open interval on which this graph is concave up and increasing. So this is a non-grapher problem, so we're going to have to do some good old-fashioned sign analysis. For the increasing part, we're going to need to know about the first derivative. For the concavity piece, we'll need the second derivative. So let's start by finding f prime and seeing where that is positive to see where f is increasing. So f prime, that's going to be, let's see, this 3 gets differentiated away. That's just 0. This next term, this is going to be 12x. And then this will be minus 6x squared. So let me set that equal to 0 and find some critical values. I can factor a 6x out of this. That leaves me with 2 minus x. And I see that this equals 0 whenever x is 0 or positive 2. So let me whip out the number line here. This is an f prime line now. And I've got critical values at 0 and 2. Let me test out something less than 0, like -1. Plugging that in this factored version here, that's a negative and 2 minus -1. We've got to be careful here. That's actually a positive. Negative times a positive is a negative. Next, number between 0 and 2, like 1. That's a positive times another positive, so positive overall. And then something bigger than 2, like 3. Positive times a negative is negative. So we see that our function f is increasing on this positive f prime interval of 0 to 2. All right, so let's move on then and figure out the concavity part of this. So let's see here. And the only answer choice you could eliminate from this would have been, it looks like answer choice D, which does not have anything in this interval. So let's move on to the second derivative now for concavity. So first derivative was this stuff here. Second derivative, going left to right, would be 12 minus 12x. And let me set that equal to 0. Now this one I don't have to do any fancy factoring or anything. Just subtracting 12 and dividing by -12, we see that x has to be 1 for this one. So set up an f double prime number line around the critical value 1. Number less than 1, how about 0? Plugging that in here, we've got 12 minus 0, which is positive. And bigger than 1, we've got 2. 12 minus 24 is negative. And we're looking for concave up. Well, concave up happens where f double prime is positive, so that's -infinity to 1. And now putting these together, I need an interval that includes 0 to 2 and -infinity to 1. Well, the only place where those overlap is on the interval from 0 to 1. If I go past 1, I don't have the concavity I need. If I go before 0, I don't have the increasing nature that I need. So 0 to 1, so that's going to be answer choice A.